Today we're going to start acids and bases, and the really cool thing about acids and bases is this is our last topic for this semester. So we will have the test for acids and bases a couple days before the final exam, which is in January, and this is November 2nd. So there's a lot of material in acids and bases. Of course, we also have a lot of days off from now until then, so a lot of breaks, which stink. We'll have no less than 3 quizzes. I'm going to try to fit a 4th one in there if I can. But today is just a nice, short introductory. Tomorrow we'll talk about pH, pOH, but today is just basic stuff. All right, let's talk about the types of acids and bases that exist. The first one is Arrhenius, and I know that's pronounced a couple different ways, so I apologize if it's not the way that you initially heard it. But an Arrhenius acid is something that, when it's placed in water, it dissociates and forms hydrogen ions. Okay? And an Arrhenius base is something that, when it's placed in water, forms hydroxide ions. Okay? So when we look at Arrhenius acids, they form hydrogen. Arrhenius bases form hydroxide. Okay? Pretty basic definition, and I think these are the types of acids we talked about in junior high or middle school or whatever you're calling it nowadays. Does anybody recall from the summer how you can determine if something's an acid or a base? Yeah, Megan?
One starts with hydrogen, the acids start with hydrogen, and
Good.
the bases end with hydrogen.
Hydrogen, very good. So it's not OH, it's actually hydrogen. So acids start with hydrogen, bases finish with the hydrogen. What if you had something like this, and this does exist? Water, very good. Is that an acid or a base? Neither?
Neutral.
Neutral? Well, does it act like an acid or act like a base?
It acts like whatever you can do.
The answer is yes, it is an acid and a base. Okay, this is called amphoteric, which we'll talk about here a little bit later. It's on the back side, but don't worry about it. So when this dissociates, it can form hydrogen or hydroxide. Okay, so amphoteric substances can act like an acid or a base. The next type is probably the one that you'll most definitely see on the AP exam, and I'll give you a bunch on quizzes and tests, is the Bronsted-Lowry acids and bases. Bronsted-Lowry acids donate hydrogen or protons, where Bronsted-Lowry bases accept them. So if I had, say, an example where I had, say, bisulfate and reacting with water, and this would form sulfuric acid and hydroxide, you should be able to look at that balanced equation and say, oh, that's an acid, or oh, that's a base, or ooh, there's the conjugate acid, or wow, there's the conjugate base. Okay? So knowing what we have and what we finish with is really important. So if I look at, say, the bisulfate, the HSO4 with the -1, did it gain or lose a hydrogen from the reactant to the products? Gained. So this is acting like a what?
Base.
A base. And I always, or I try to draw the arrow from the source. In other words, if I look at water here, it has 2 hydrogens where it only has 1. So this is acting like a acid. Okay. And then on the flip side, if we're going in this direction, okay, we have 2 hydrogens here where we only have 1. So what did this do? Donated a hydrogen. So on this side, the sulfuric acid is acting like a conjugate acid. Good. Okay. Now conjugates are only on the product side. Conjugates are on the product side. Acids still behave like acids. They donate hydrogen, okay, whether it's conjugate or regular. And bases, whether it's regular or conjugate, always accept those hydrogens. Oop, CD. Okay. Let's give you another example.
If the top one is written the other way, would it be?
You mean as these 2 are reactants
Yeah.
and these 2 are products? then whatever's on the reactant side is acid or base. Whatever's on the product side for that given expression or that equation. Yeah, so don't, and I know it's easy to say, okay, well, I'm going to throw those away. I'm going to bring these over here and reverse it, depending on how it's presented to you. Treat it like a reactant or product. Okay? If I were to ask you who's the conjugate base, your response would be? Conjugate base. Is what? OH, good. And here's how you do it. And this is pretty typical of how the AP exam, you'll have a question like that and it'll say A, well, it'll be like this, it won't be water. When we have water as both the acting as an acid and a base, keep them respective. In other words, the first one goes with the first one on the product side, the second one goes with the second one. Okay, keep it respective. Here, I can flip-flop these on the product side because we have a plus, just means and hopefully you realize that water is not going to change into sulfuric acid. All right, but here we want to look at the respective things. So water, here we have 2 hydrogens, here we have 3, so what did this do? Did it gain or lose? Gain. So we accepted a hydrogen there. So this is acting like a what? Acid, and this is the base. So to get it back, then the H3O plus is acting like a
Conjugate acid.
and there's your conjugate base, the hydroxide. Okay. What's the matter, Richie?
I missed what you did on the last side there.
On the what side? This one?
Yeah. how'd you
Okay.
do
These two represent. This is the before for this. This is the after for that. Okay. So here I've got 2 hydrogens. Here I have 3. So that means that this other thing gave it a hydrogen, so it went from 2 to 3. To get back to the other side, it needs to give it away. So now we're back to 2. We're back to go. College Board sent this document out about 2 weeks ago because they're changing the format of the exam again. And what they're doing is they're saying what's going to be on the exam and what is not going to be on the exam. So the next thing that's listed on the types of acids and bases is Lewis. Now, on your notes, I don't think I would scribble it out completely because your college professor may want to talk about acids and bases, Lewis acids and bases, but you will not see it on tests, quizzes, or the AP exam. Okay, so, and I won't show you this every single time whenever I say, hey, omit that. Just realize that I'm reading on what is going to be omitted from the AP exam. KA, go ahead and take your equation sheet out. And on the section that says equilibrium, and I find this very ironic. Okay. Now when you look at the equilibrium section, all but the very last thing, the Kp equals KCRT delta N, which we talked about on the last test / quiz, everything else is acid and base related. So that tells you how much equilibrium on the AP exam is going to be acid and base related. So the expression, which is the very first one I believe, is this. And Ka means your acid, your constant, still your constant. Probably some things that we need to explain is what the heck is A minus? What is that? It's not an acid. It's your nonmetal or your anion. Okay, so this is your anion. So anything that has a negative charge is considered to be a nonmetal. Anything that's positively charged, we consider that a metal. So there's your metal, your nonmetal. Well, our metal that we care about with acids is hydrogen. So our generic equation looks like this, and it's very generic. Ooh, it's supposed to be an A. Okay. So HA is your acid with your hydrogen and your anion. And then when we dissociate it, it forms hydrogen ions in the anion. So an example could be, something that looks like this. Okay. So here we have the acid and hydrogen dissociates from the anion. And do realize that the charges need to get, the hydrogen will always be a +1 charge. The charge over here could be negative, could be -2, could be -3, could be neutral, okay? It just is more negative on this side and on the left side. Okay, and I'll give you an example for that today. Also, if you see the double arrow, this represents for a weak acid or a weak base. Probably better represents for weak, which we'll talk about here momentarily. Okay? Weak means it does not dissociate 100%. Okay? And in most cases, like acetic acid, I think it only dissociates about 8%. So if I have a 1 molar concentration, only 8% of that's going to dissociate from the original. If you have a strong acid, this is a nice little segue. If you have a strong acid, it dissociates 100%. Notice the arrow. It's a one-directional arrow, where the double arrow means that we're at equilibrium. So reactants form products, products form reactants. If it's 100% or strong, everything dissociates and forms hydrogen in the anion. So if I start off with a 1 molar solution of this strong acid, what will my concentration of hydrogen be at the end? 1 molar. And my anion will also be 1 molar because it's a 1-to-1 ratio. What will the HA be at the end? 0. Okay, so we won't have any. You don't make ice charts for strong. Okay, we will when we do buffers, but not for. We also never ever use an expression for a strong. I want to write that down. Never use the expression for a strong, because if this goes to 0, how do I mathematically plug that in? It's not pretty. Okay. Also, this means that the system's at equilibrium. This is not an equilibrium. This is a one-directional shift. The reactants form products, period. Okay? So the single arrow represents for a strong acid or a strong base or even a strong salt, which we won't talk about this topic. But strong means it dissociates 100%. Weak means it does not dissociate 100%. Okay? Also, let me see here. This. There's another way to write this equation or this expression, which is not on your equation sheet, but you may see it on the AP exam. I could say, actually let me erase that weak part there. I could have HA plus water, which is a liquid, forming H3O plus in the anion. The bad news is these represent the same exact thing. These are the same exact thing, except your expression for the second one would look something like that, except you'd have H3O plus. Okay. So what that means is hydrogen ions are the same thing as H3O or hydronium. Okay. Those mean the same exact thing. What we don't do on this one, and you could if you wanted to, you could write water right above the double arrow, which means that it's dissociating in water. All of these will dissociate in water. Here we're actually saying there's the water. Where would water appear in the expression? Or why don't I have water in the expression? Probably the better way to say it.
It's the base.
No, it's a liquid. Liquids and solids never appear in the expression. However, if you do include water here, we have to balance out the atoms, so that's why we have H3O plus. Okay, so that's all it's saying is there's a hydrogen with the water. Yeah, Danielle?
Well, I don't understand what the H, can that be anything?
The H?
Like,
No, it's a hydrogen ion.
always gonna be?
Yeah, oh yeah. The anion could be anything. That could be whatever's attached or in front of the hydrogen, or I'm sorry, behind the hydrogen. Yeah, the H is going to be an H, because what makes something acidic is one of these two things, the hydrogen or hydronium. Okay. All right, so are we good with strong and weak? And again, all I'm doing is talking about the acid today, but I could talk about bases. Strong means it dissociates 100%, weak means it doesn't. And do take note on the types of arrows that I have on there. Okay, strong is one directional, weak is double. And expression. So these are only for weak. All right. This is an example of what kind of acid? Mono or polyprotic? Mono. Mono means one, and protic means proton. Okay, so if I look at the hydrogen ion that has no electrons, that's a proton. So that's where they come up with the protic. Here's an example of a polyprotic. Okay, and what I want you to notice here is only one hydrogen dissociates at a time. Okay, so it's always one step. And later on, I'm going to tell you that's as far as we go whenever we do calculations for pH and pOH. Okay, so polyprotic just simply means we. All right, on the back side, I've got a table there that kind of gives a brief description on some of the things. You can look at that at your own leisure. Water as an acid or a base. Okay, we talked about that as being amphoteric. Water's the most common amphoteric. I will give you a bunch of them. You don't have to know that they're amphoteric, but you'll be able to recognize it. Okay. The next thing is Kw. If you look on your equation sheet, it's the third down in the equilibrium section, the Kw expression. K, again, represents your equilibrium constant for pure water, and it's the hydrogen concentration times the hydroxide concentration, and that all equals 1.0 times 10 to the negative 14, and that's at 25 degrees, I believe. Yeah, at 25 degrees. So when we look at a sample of pure water, if I knew what the hydrogen concentration is, I can find out what the hydroxide concentration is. And we'll use this tomorrow for pH, pOH.
Okay, yeah, that's the pH is 14.
We'll talk about that with logs tomorrow. Don't let it out of the bag yet. If your hydrogen concentration is greater than your hydroxide concentration, what can you say about the solution? It's acidic. And if your hydroxide is greater than your hydrogen, basic. And if they're equal, then it's neutral. Good. And I think you guys, I hope you learned that in General Chem. All right, so let's look at some examples here. Calculate the hydrogen or hydroxide concentration that is required for each of the following solutions at 25 and state whether the solution is neutral, acidic, or basic. So in A, and then write the expression. So we have, oh, I'm sorry, that's for the next part, my bad. We have hydroxide. That's equal to 1.0 times 10 to the negative 5, and it wants to know what is the hydrogen. All right, so since we know the hydroxide, we're going to move it across, equal sign. So what we'll have is 1.0 times 10 to the negative 14 divided by the hydroxide. And it's 1.0 times 10 to the negative 5. And make sure your calculators can get this for you. Okay. Today's a great day to make sure that the calculator's doing what it should be doing. And if you can't get that, definitely let me know. All right, so there's my hydroxide concentration, there's my hydrogen. Is this solution in part A acidic or basic? What is it? Acidic? Why? The H plus is higher? Why is it higher? It's not, it's lower. The negative 9 means that that's a smaller value. So the hydroxide's higher, so this is a basic solution, right? Okay. Remember the negatives, it's like saying that I have 8 zeros and then the 1. And then this is only 4 zeros and then the 1. All right. Part B, we have hydroxide, which is 1.0, 10 to the negative 7. So hydrogen, we're still going to use that same equation there. So did anybody get 1.0 times 10 to the negative 7? Okay. Is that acidic, basic, or neutral? Yeah, Sam, I'm sorry.
Okay, wait, why did you put one on top of the other one?
Okay, so here's our equation right here. And if the one that I know, I want to move diagonally, put below the constant. So the 1.0 times 10 to the negative 14 should always be on top. And if we're looking for one of these others, one of these should be known. So the hydroxide was given, so I want to move it diagonally, or divide it on both sides. So I have that divided by that, and I can find that. And since I gave this value here, basic, neutral, or neutral? Since they're the same, they're equal. And the last one, I think it's hydrogen, is that 10?
Yeah.
Okay, so the hydroxide, and what we're doing here is we're going to divide both sides by the hydrogen since we know the hydrogen. And we're looking for the hydroxide. So 1.0 times 10 to the negative 14. And it's 10. Anybody get negative 15? Okay.
That's impossible.
It's impossible?
It's impossible.
Why?
Because they add up 10 to the negative 14.
Not impossible. Just a really low concentration. We can't have pHs that are greater than 14 and lower than 1. We just say that the range is 1 to 14.
Wait, what?
Tomorrow when we talk about pH, you're thinking that that's not a good value.
Yeah, but
It's not bad.
okay.
It's legal.
That's really acidic.
So is this acidic or basic?
Really acidic.
Now, I had somebody in last period say, ooh, if I look at that 10 molar acid and compare it to that 1.0 times 10 to the negative 9, that the 10 molar is a stronger acid than this acid, correct?
Wait,
This one's stronger than that. Yeah?
no, wait.
This one's stronger than that, right? Throwing you a curveball, seeing if anybody hits it. Cold Chicken said no. What's the matter, Sarah? You look uncomfortable now. Sonali's about ready to bash her head in on the desk. True or false? This 10 molar solution is stronger than that 1.0 times 10 to the negative 9.
The 10.0.
What does stronger mean? Good question.
Like, do you mean stronger acidically or stronger like do you
Okay,
mean-
yeah. What does strong mean? What is the definition of a strong acid or strong base or a strong salt? Shh, go back to sleep. Strong simply means it dissociates 100%. Is there any way to tell how much this dissociates? No. And somebody was using that saying, oh, since it's got a higher molarity, that means it's stronger. No. What this means is that 10 molar is going to burn you a lot more than this 1.0 times 10 to the negative 9. Burning effectiveness has nothing to do with strength. Okay. The concentration just means, okay, the higher concentration means there's more hydrogen ions. These are the things that like to burn you. Actually, the hydroxide, if it's high enough, will burn you as well. Okay. So strength has nothing to do with concentration. Yes, sir.
Why is there no labels on this?
Why are there? Because I'm a bad guy. There.
Is the H plus more acidic? Like the 10 molar?
Is okay. Ask that again. Is this? Oh yeah, it's much more acidic. Yeah, that's why it's an acidic solution.
But it's not stronger.
No, strength has nothing to do with it. All right, example part 2 says write the dissociation equation for each of the following weak acids. So I actually told you it's weak, so that tells you what kind of arrow you're going to have, or arrows. And then write the equilibrium expression. Okay, so we've got propanoic, and you won't have to ever name this. This will be given to you, since it's not from one of your 10. Actually, it only qualifies as 7 of those polys that make acids. Okay. So since it's weak, double arrow. And how will this dissociate? H plus, very good. Excellent. And this is the anion. Okay. Looks like the makings for a good ice chart, huh? Huh? And then the expression would be your products over your reactants. And we're going to be doing lots and lots of ice charts. I think I even, oops, not 7. I think I told you guys that the first day of ice charts. Okay. Let's pretend that we're actually putting this in water, and you want to write water. Because sometimes the test, quiz, or AP exam may do that to you. So nothing changes charge-wise. Okay, it's still +1 charge. The only thing that changes on the expression is right here. Okay. So H3O plus, and I'll only do this for this first one.
And the water acts as a base?
No, water does not act like a base. Unless you're talking conjugate acid, conjugate base.
Yeah.
Yes, I'm sorry. Yeah. Yeah, Sam.
So what's the difference in doing that? Like, is there
Technically speaking, there's no difference other than if you're asked to identify conjugate acids and conjugate bases. Here, you wouldn't be asked about conjugate acid and base. Here we would. On an ice chart, what would you do for these? Dash them.
Does it know what the point of doing that was?
You're going to see that probably on the AP exam. I've seen it quite a bit where they'll either give it to you like this or like that. And what's crazy is on the equation sheet they give it to you like this, where it's H plus the A minus, and it doesn't have the hydrogen in there. But
I don't know if there was like a certain time when we would need to do that.
the time to do it is when they give you water. If they don't give you water, it's your call if you want to do it this way or that way. It's artistic interpretation. How's that? Feeling it? I'm not. All right, the next one. What is that? Nitrous?
That's all we need to do?
Yeah. Write the dissociation and then the expression.
That's awesome.
Yeah, we're not doing any equations today. Tomorrow we will, or whenever we meet again. Sorry. HNO2. You want to do it the top way or the bottom way? Top way.
Top way.
And there's nothing wrong with doing it either way. Okay, so there's the equation, the expression, and do include the charges. I know that some of us get kind of lazy and not write the charges. The charges are very important. Okay. And then the last one, chloris. Now you guys still remember how to name acid, right? I think we did it back in July. Like, yeah, you'll have to. Oh yeah. Name acids. Soon, maybe today. That's all review now. Yeah. Like if you have per, what does that mean? Huh? One more oxygen than it came with. Hypo means what? 2 less. Very good. The ite means 1 less. Okay. And I'm trying to remember, it was early on. Couldn't have been like somewhere between day 2 and day 8.
Yeah. It's like perchloric acid.
Yeah, you'll get that. So chloris. CO2.
Oh, that's 4. No, it's 5.
No,
Yeah, 'cause
it is not 5.
it's 4.
Yes. Chlorate's 3.
Yeah, so I thought you had 2 more.
1. Per is 1.
hypo's two but less.
Hypo's 2 less.
Wait, and that's oxygen, right? All those-
Yeah. And remember, if it ends in OUS, that means that we had an ite at the ending of our poly.